Okay, you're welcome to today's lecture. Okay, in the last class, we looked at one-way analysis of variances, which is used in investigating the differences in two or more population means. Today, we want to proceed with correlation and regression analysis, as well as the chi-square tests, okay, or the chi-square analysis. Okay. So we're looking at an introduction to correlation and regression analysis. Specifically, we'll be looking at simple linear regression. Okay. Now, when we talk about correlation, okay, then we are talking about relationship. Mm. So in correlation analysis, we are examining the relationship between two variables. And in life, a number of variables are related. For example, height and weight, time of study and performance, weight and speed, okay, and other several variables. So correlation analysis helps us to identify the type of relationship among variables, okay, and then two, also the measure of this relationship, okay, and also the direction of the relationship among the variables. Now, key things we need to note is among variables, there can be situations where one variable could cause the other, okay, or could predict the other, okay. And in such cases, the variable that predicts or is capable of influencing the other is referred to as the predictor variable, okay. Whereas the factor or the variable which is influenced, okay, is referred to as the dependent variable. So let's take, for example, time of study and performance, okay. Clearly, your performance will determine on how much time you take in what? In studying, okay. So which means that your time of study, okay, leads to your performance or causes, influences what? Your performance. So we refer to the time of study as your independent variable, okay, the independent variable, and then we refer to performance as what? The dependent variable, or in short, DV. Okay, good. Now moving on. Correlation can be examined using plots, or specifically scatter plots. And then we can also examine the correlation using summary statistics, okay, which can help to describe the correlation among two variables, specifically to quantify, to give us a measure of the amount of the relationship. Whereas the scatter plot helps us to know the type of correlation, okay, and to understand the degree, okay, of the correlation, okay, but does not give us a measure or a quantity, okay, to a statistic value, which will help us to quantify the amount of relationship. Okay, so let's look at scatter plots. Like we said, they help us to display the relationship between two variables, and they are always useful in the early stage of analysis when exploring what? Data, and determining if a linear regression is what? appropriate, okay, for further analysis. Now, in scatter plots, we plot our independent variables on the x-axis, okay, on the x-axis. The independent is usually your x, and then your dependent variable is the y. Okay, and we can have about 4 cases, okay, of plots. The first scenario is when you have, let me use a scale first, 1, 2, 3, 4. Then I have 1, same here. So we have 1, 2, 3, 4. Okay. Now, if we have data sets, okay, which help us to plot, maybe we have 1, 1, 2, 1.8. We have 3, let's say 3, 3, or 4 something. Okay. Yeah, we'll realize that there appears to be a pattern, okay, with these data sets once it's been plotted. And it is possible to fit a line of best fits, okay, to this data points. So if we are to plot a line of best fits through this data points, okay, it's going to be what possible. Okay, so it helps us to tell, or it helps us to know that a linear relationship would exist among these data sets. Okay, now another type of graph we can have could also be observations going this way. We have x, y. Okay, and then we can also have a scenario where the data looks like that. Okay. Then we can also have a scenario with this kind of plots. Okay. Yeah. So when we look at this, we can tell that for the first 2 graphs or the first 2 plots, okay, there appears to be linear pattern among the variables. Now let's take them one by one. If there is a linear relationship in the first figure, okay, let's assume we plot that straight line to the data. If we are to find the slope of this graph, then this slope should give us what? A positive slope, or a positive what? Gradient, okay? So we say that the relationship that exists here is a positive relationship or a positive correlation. Okay, now what does positive correlation mean? Positive correlation simply means that whilst your independent variable increases, okay, your dependent variable also appears to what? To also what? Increase, okay? So when we move from 1, y is 1. When you move to 2, y also increases to 2. When you move to 3, y increases to around 2.8. When you move to 4, y increases to around 4.1, okay? That is a positive correlation. So whilst independent increases, dependent also increases. Now, in this plot, which is figure 2, okay, here, if we are to fit a straight line to this point, a line of best fit to this point, okay, and find the slope, we'll get a negative slope or a negative gradient. Okay, so we say that this graph here, with this graph here, let me use R. In this graph here, our correlation is going to be a negative figure, okay? It's going to be a negative value. So we say that the data points are, or the variables are negatively what? Correlated. Now, when we talk about negative correlation, what will be? Negative correlation means that whilst your X is increasing, Y rather appears to decrease, okay? So if you had 1 here, 1 corresponds to around 4 here, okay? But when you come to the tail end where X is around 4, we are rather having Y to be 1, okay? So negative correlation means whilst X is increasing, Y is what? Is decreasing. Then in this plot here as well, okay, we can clearly see that there is no linear pattern to this data. There you cannot fit a linear, okay, pattern to this data. So here your R value is equals to 0, meaning there is no correlation at all, no relationship, okay? Good. And again, we could have this type of data, okay, where we cannot confirm a linear relationship. We can see that even though there is a pattern to the data, the pattern is nonlinear, okay? The pattern is nonlinear, okay? So such a data set cannot be modeled using what? A linear regression, unless the data is transformed, okay, into a linear data set, okay, using some transformation techniques. Okay, now for the figure 1 and figure 2, okay, what you have to know is the closer the data points are, the closer the data points are to the line of best fit, okay, the stronger the value of what? The correlation coefficient, okay? So the closer our data points or our data sets are, the stronger your R value, the correlation coefficient. So the more dispersed the points are from the line of best fit, the weaker the correlation will be, okay? So what we are saying is, if you have data sets like this, okay, your R here will be less than the R value in the first case over here, okay, figure 1, because these points are very close to the straight line compared to this other one. And it's the same in the case of the negative correlation. So if you have more dispersed points around what the central line, okay, then we can say that even though there's a correlation, the correlation is weaker compared to the scenario where all points appear to lie on the what? On the straight line. Now, when all points lie on the straight line, we call it positive what? Either a perfect positive correlation or a perfect negative correlation. Okay, let's move on. Good. Now, so that is for the scatter plots. So scatter plots first help us to know whether there is a relationship among data points or among two variables, and also the direction of relationship. But like we said, it is limited in the sense that, okay, it does not give us a measure of the amount of relationship between the two variables, okay? So it's limited to explorative studies. Usually we use scatter plots as exploratory analysis for regression analysis. Okay, good. Now, another measure which we talked about earlier is the correlation coefficient. Okay, the correlation coefficient. And for scaled variables, okay, yeah, we can estimate what we refer to as the Pearson's correlation coefficient or the product movement correlation coefficient R. Okay. So we are saying that the linear correlation coefficient measures the strength and the direction of the linear relationship between the two variables. Okay, good. And a very simple computational formula for R is given in the formula, like we can see, which is n summation xy minus summation x times summation y over the square root of n summation x squared minus summation s squared times n square root of n summation y squared minus summation y all squared. Okay, and what you need to know is n is the number of data points. Okay, the data pairs for x and y, and then the value of the correlation coefficient always lies between -1 and +1. Okay, where negative means we have a negative correlation, positive means we have a positive correlation, but r equals to 0 means there is no correlation at all. Okay, like we saw earlier in the scatter plots. Okay, so moving on, we're expected to have calculators by us, okay, and also have the formulas to guide you to understand the examples we'll be looking at. So try and copy the formula and get your calculators too. Now we have an example. Okay. Yeah, so we have an engineering firm here, which is Kantanka Automobile, advertises extensively on TV, emphasizing their low prices and easy terms of payment. The owner would like to review the relationship between the sales they make and the amount they spend on advertisements. Below is the information on sales and advertisement for 4 months. Okay, so we have data from July to October, and then we have data for advertisement, amount spent on advertisement, and then amount spent sales, okay, revenue, which is made. Now, like we said from the beginning, okay, anytime we have two related variables, there are scenarios where one variable influences the other, okay? So in this case, we can clearly see that the sales that is made, the revenue that is made, okay, will depend on how much advertisement they make. So we are looking at a relationship where advertising expenses is the influencing factor, that is the predictor variable, okay? And then the revenue is the dependent variable, that is the factor or the variable which is what influenced. Okay, good. So this is your x, and then this is your y. Good. So this is the first step in the analysis. You first need to identify which of the variables is your predictor and which is your dependent variable. Okay. Now moving on. So in the solution to the problem, the formula, like we saw, requires that we have a component which is summation xy. Okay, xy means you have to multiply the data observation for your predictor, okay, and then the observation for the dependent. So you multiply it. So xy here is going to be 2 times what? 2 times 7, okay? That gives us the 14, which we are seeing here, okay? Good. Then you do same here. That will be 1 times what? 3, which gives you 3. 3 times 8, which gives you 24. 4 times 10, which gives you 40. And then 10 times 28, which gives us what? Oh, sorry. I think it ends at October. Yeah, so this is for the total. Okay, then you find the summation. So this quantity here is summation x, y. Okay, good. Then also you need summation x squared. That is the sum of the squares of x. Okay, so you have to go and find the squares of x and then sum it up. Okay, go. So we square x, that will be 2 square. This is 2 square. This is 1 square. This is 3 squared. This is 4 squared, okay, which will give us 16. Then after that, you sum everything to give you a summation what? Summation x squared, okay. Then also we have y squared in this formula here. So you square y, that will be 7 squared, we have 49. 3 squared is 9. 8 squared is 64. 10 squared is what? 100. Then you sum it up. So summation here, this is the summation of y squared. Okay, so when we fuse these values into the formula, okay, that is going to give us what? 4. Now our pairs of data was for 4 months, so we have 1, 2, 3, 4. Okay, so your n equals to 4. N is equals to 4. Okay, so when we substitute into the equation, we get 4 times what? Summation xy, which is 81, minus summation x, which is what? 10, times summation y, which is 28, all over the square root of n is 4, x squared, this is x squared, 30, okay, 30, minus summation x, which is 10 square. This square affects just this 10, take note, times the square root of 4 into bracket summation y squared. This is y squared. So we have 2 minus 28, which is summation y square. The square once again affects just summation y. Okay, so once you do that computation, you would get 0.964. Okay, so you can verify that quickly before we continue. Yeah, so now that we've verified and obtained the answer, okay, the question is, how do we interpret the correlation coefficient we just obtained? Okay, in interpretation, like we said, R always lies between -1 to positive 1. Okay. Now the scale of interpretation, mm, hmm, on the positive side, we could have 0.3, 0.5, 0.7, okay, 0.99, or let's say to 1, okay. Then similarly, you have on the other side, that's negative 0.3, okay, negative 0.5, minus 0.7, and then we have 1 here, negative. Okay, so let's concentrate on the positive side. Okay, now when the value you obtain for R lies between 0 to 0.3, we're talking about a negligible, okay, negligible positive a negligible positive correlation. Okay, positive correlation. Then when we come here, we're talking about a moderate positive what correlation, a moderate positive correlation. Then in between these two values, we're talking about a strong correlation, a strong positive correlation. Okay. And then over here, we're talking about a very strong positive correlation. So very strong positive correlation. Okay. Very strong positive correlation. And then when we have 1, we have a perfect positive what? Correlation. Okay. Good. So that also applies to the other side, of the graph. Okay. So over here, this will be negligible what? Negative. This will be moderate negative correlation. This will be strong negative correlation, and then very strong negative correlation, and then negative, perfect negative correlation. Okay. So per the value we've just obtained, which is our R equals to 0.964. Okay, if we compare with our scale here, then we are saying that then there is a very strong positive correlation between what? Advertising expense and revenues after what? After sale. Yeah, that is how we do the interpretation. Now I'll take 1 or 2 questions from you, if there is any, before we continue. Now, after you've estimated your correlation coefficient, okay, that is not enough. You may want to further investigate whether this correlation is indeed significant, okay? Or what we mean by significant is the correlation is not close to 0. You understand? There are many situations which calls for this test. One scenario could be obtaining data sets. You see, the idea here is we are talking about linear relationship. Okay. Now, if you have data sets which the scatter looks like this. It is possible that after you've calculated your R, you may get a value, okay, a value of, let's say, 0.36, okay. But the question is this R value, okay, indeed significant, okay? Is it indeed a significant linear relationship? Because your scatter is telling us this is not linear, but you calculated and you got this. Again, we can have field data, and usually in field data, you can never get a perfect correlation. So some of the theoretical values or the theoretical scale we just looked at may slightly differ, okay, in interpretation, because you will never get an R of 1, okay. For some data sets, the best value you can get for R may even be less than 0.8, okay. So there is a need for further testing of the correlation which you've estimated. And to do that, we employ a hypothesis testing technique. So like any hypothesis testing technique, step one, you have to state your null and the alternate hypothesis. So in this case, the null hypothesis says your R, either your R or sometimes we use rho, okay? So rho is equal to 0. If it's 0, then it means there is no correlation. And then rho is not equal to what? 0. Then step 2, you select your significance level, which we already are aware of. Step 3, okay, you select your test statistic. Here, our test statistic is going to be the student T statistic, okay, given by R, the correlation coefficient, times the square root of n minus 2 over the square root of 1 minus R squared, okay, where n minus 2 is the degrees of freedom. Then once you've calculated or you've, yes, picked data to compute the test statistic, which theoretically is the fifth step here, okay, good. You also have to formulate a decision rule. And the decision rule, like we said, we are applying the critical value approach, okay. So you read, depending on the value of, on the sign on the alternate hypothesis, okay. If it's a one-tailed test or a two-tailed test, you take that into consideration. So you read your critical value, and then decide on whether to reject the null hypothesis or not to reject the null claim, okay, and then you conclude as usual. So in relation to the example we've just looked at, okay, this will be the computation. You have your null hypothesis, you have your alpha value, you have your T statistic, okay. So you fix in your 0.964 times the square root of 4 minus 2, because n was 4, okay, divided by the square root of 1 minus R square, which should give us 47.86, okay. Then we read what the critical value, we have T with what n was 4, so we're going to have 2, okay. So when you read it from your table, check from your statistical tables for me. Yeah, so from the statistical table, we are dealing with a two-tail. Okay, so we have alpha as 0.025, and the degrees of freedom was 4 minus 2, which is 2. Okay, so the point of intersection is what? 4.303. Okay, so that is the critical value. Now moving on, this tells us that we have, sorry,
Sir,
yes,
the alpha was 0.05, not 0.025.
yes, but you have a two-tailed test.
Okay, okay, sir.
Always remember, okay?
All
So
right,
you
sir.
always check the sign on the alternate hypothesis. So when
Okay,
you
sir.
read, that gives us our critical values. And then the final stage is always to compare. Now, when we compare this on the scale, that will be to the extreme right, okay? That will be to the extreme right of the graph, okay? So, which means that uh, the test statistic value falls in the rejection region. If it falls in the rejection region, then we have evidence to reject what? We reject the null hypothesis, right? We are rejecting the null hypothesis. So we reject H naught. Okay, so we're rejecting what? The null hypothesis. Okay, if we've rejected the null hypothesis, then we are saying that indeed the correlation coefficient we estimated is not equal to what? Zero. Okay, it is not equal to zero. So it's not equal to zero means that indeed we have a linear pattern in the data, a linear relationship in the data. Okay, and that correlation, which was a strong correlation, is significant. That is what we mean by this test. Okay, let's take another example if there is no question. So I would like to introduce the regression analysis. Okay, then before we take the second question. Now, so like we said, in correlation, we are just referring to the relationship among the two variables. Okay, but regression analysis goes beyond that. In regression analysis, we are trying to find the linear model, okay? The linear model uh, which can be used to make predictions about the observed data sets, okay? So we have the data set, we have the scatter, we know that there is a linear pattern here, okay? But can we make predictions based on an empirical model, okay? A model, I mean, a model built on these observations. So we call it an empirical model, okay? Good, and such a model is derived, okay, from the least squares procedure. It's derived from the least squares procedure. So this model gives us the best fit with the least square deviations of observations from the the line of best fit. Okay. So it's a very good model because it gives us the least squares of deviations of point from the regression line. Okay. So this regression line like you can see, it's a linear equation. So once it's a linear equation, we're talking about a linear function y equals to mx, okay, plus a certain what? A certain b. You understand? So we say that the estimated value of our dependent variable based on this model, okay, is giving us beta naught, which is your b in this case, plus beta 1 plus x, okay, where your y cap is the predicted value of y, a model that is based for predictions, okay, good. Then we have beta naught is the y-intercept, that is when x is equal to 0. This whole term will go to 0, okay? So then y estimate will become beta naught, so it's the y-intercept. And the beta 1 is the coefficient of the predictor